This video is for Chemistry in the Earth System, Unit 5.2, Solutions. Today's essential question is, what are the various colligative properties of solutions? Today, we are going to explore an important concept in chemistry, colligative properties. These are the properties of solutions that depend only on the number of particles that are dissolved, but not on the type of particles. This means it doesn't matter if we dissolve sugar, salt, or antifreeze in water. What matters is how many particles are present in the solution. This concept is central to understanding how solutions behave, especially in the real world. For example, we'll learn why adding salt lowers the freezing point of water, why antifreeze prevents car engines from freezing in winter, and how colligative properties help us explain biological processes like osmosis in cells. Colligative properties are special because they depend on the quantity of solute particles in a solution, not their chemical identity. Whether you dissolve table salt, which is NaCl, or sugar, which most common types are C6H12O6, what matters is how many solute particles there are. For example, when NaCl dissolves in water, it splits into two ions, Na plus and Cl minus. That's why we say the Van 't Hoff factor, I, for NaCl is approximately 2. If we dissolve a compound like CaCl2, calcium chloride, it splits into 3 particles, 1 calcium ion and 2 chloride ions, so the value for I would be 3. On the other hand, a molecular compound like glucose does not split apart. It stays as a single particle, so for glucose, I would equal 1. This difference in the number of particles helps us understand why a 1 mol solution of NaCl has a stronger effect on colligative properties than a 1 mol solution of glucose. So let's begin with vapor pressure lowering. In a pure solvent, like water, molecules at the surface can escape into the air as vapor, creating vapor pressure. But when we add a solute, like salt or sugar, the solute particles break up and they take up space at the surface, which reduces the number of solvent molecules that can escape. This is why adding a solute to a solvent lowers the vapor pressure. It's a physical blocking effect. In a closed container, these solvent molecules bounce around, but fewer of them can leave the liquid and enter the vapor phase because some of the surface area is blocked by the solute particles. This is the foundation of two important colligative properties: boiling point elevation and freezing point depression. So let's talk about boiling point elevation. When we add solute particles to a liquid, it's harder for the liquid to boil. Why? Because the solute particles interfere with evaporation, requiring more heat energy for the solvent to escape into the gas phase. This means that the boiling point increases, a phenomenon that we refer to as boiling point elevation. This relationship, this boiling point elevation, is described by the formula delta T sub B is equal to I multiplied by K sub B multiplied by M, where the delta T sub B is the increase or change, that's the delta, in the boiling point. That's why it's T sub B, it's boiling point temperature, the temperature of the boiling point. So it's the change in the boiling point. We've already mentioned that lowercase I represents the Van 't Hoff factor, and the K sub B is the boiling point elevation constant, which is something that you will be given in calculations. For example, for water, it is 0.512 degrees Celsius, kilograms per mole. That lowercase m still represents molality, which remember is moles of solute per kilogram of solvent. For example, if we dissolve salt in water, the salt dissociates, increasing the number of solute particles, so the boiling point rises. This is why adding salt to water when cooking pasta makes the water boil at a slightly higher temperature. Now, let's talk about freezing point depression. When we add a solute, like salt, to a liquid solvent, like water, it becomes harder for the water molecules to lock into a rigid grid like a solid. The solute particles therefore disrupt the crystal lattice that forms during freezing. So, the solution freezes at a lower temperature. This is why salt is spread on icy roads in the winter. It lowers the freezing point, which makes it harder for ice to form, keeping the road safer. Now, the formula for freezing point depression is very similar to the formula for boiling point elevation. We're simply using different values. So, notice the similarities, but also notice the differences. So we have delta T sub F is equal to lowercase I, which is multiplied by K sub F multiplied by M. Now for water, K sub F, right, which is going to be the freezing point constant, is going to be 1.86 degrees kilograms per mole for water, right? Again, that's just for water. So let's apply this to an example. If you dissolve 12.55 grams of NaCl into 180.4 milliliters of water, which by the way has a density of 0.9941 grams per milliliter, we can calculate the molality as follows. First, we'll convert the the grams of NaCl into moles, because remember, when we're getting that molality first, we need it moles divided by kilograms. So we need the moles of NaCl, not the mass of NaCl. So we'll use the molar mass of NaCl as a conversion factor to convert the 12.55 grams into a molar value, which happens to be 0.215 moles. Then we're going to find the mass of the water, because again, molality is moles per kilogram. Given by this particular example, a volume of water. So in order to find the mass of the water, we're going to multiply the volume of the water by the density, which again, in this sample we've been given, it's the 0.9941 grams per milliliter. We're going to multiply those values to get a value of 1.793 grams. But again, molality is moles per kilogram. So I'll do one more step. I will convert that 179.3 grams into kilograms, making it 0.1793 kilograms. So now that we have a mole value and a kilogram value, we can calculate the molality. It's going to be the 0.215 moles divided by the 0.1793 kilograms, which will give us a molality of 1.20 moles per kilogram. So now that I have that value for that lowercase m, I can plug that value into my equation. Delta F is equal to I multiplied by K sub F multiplied by m, which substituting in, I'll have 2 multiplied by 1.86 multiplied by 1.20, which is a value of 4.45 degrees Celsius. So the new freezing point is going to be 0 degrees Celsius, because that was the old freezing point, minus 4.45 degrees Celsius. So my new freezing point will be negative 4.45 degrees Celsius. Let's move on to osmotic pressure. Osmotic pressure is the pressure created when a solvent, like water, moves across a semi-permeable membrane toward a solution with a higher concentration of solute particles. The membrane allows only certain particles, like water for example, to pass through. And at the same time, it blocks solute particles. This movement continues until the pressure difference balances out the concentration gradient. Osmotic pressure is calculated using the formula pi is equal to mRT, where pi is the osmotic pressure, capital M is the molarity, capital R is the gas constant, and capital T is the temperature measured in Kelvin. By the way, it's not degrees Kelvin, it's Kelvin. Osmosis, remember from biology, is essential for many biological processes, like how plant roots absorb water and how kidneys filter blood. Colligative properties are all around us in daily life. Think about antifreeze in a car's radiator. Ethylene glycol lowers the freezing point so the liquid doesn't freeze in cold weather. Or consider how salt is used to melt ice on roads in winter. By lowering the freezing point, it prevents ice from forming even when the temperature drops below 0 degrees Celsius. In biology, osmotic pressure helps plants absorb water from the soil and maintain turgor pressure in their cells. Even in food preservation, high salt concentrations create a hypertonic environment that dehydrates bacteria by drawing out water through osmosis, which helps prevent the spoilage of the food. At this point, you should be able to generate a full and appropriate response to today's essential question: what are the various colligative properties of a solution?